Push that rock with Simpson math. Let's talk about mappings, or to use a more traditional term, functions. First, let's discuss Pascal's triangle. We start with the 1, and then we create a triangle of 1s, and we keep adding rows to this triangle so that it gets wider at the base by adding 1s on the ends and then putting a number here that is the sum of the numbers above. So 1 plus 1 is 2, and 1 plus 2 is 3, and 2 plus 1 is 3, and 3 plus 3 is 6, and so forth and so on. So there's a 1 over here we can't see. Okay, so we put 1s on the ends, and then we fill in these gaps. 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4. So the next row would have 1s on the ends, and then put 1 plus 4 is 5, 4 plus 6 is 10, and then 10, and then 5, and so forth and so on. And this construct is called Pascal's triangle. It's an ever-expanding triangle. Now, here we have it. It may be a little too small for y'all to see, but hopefully you'll make sense of it. We call this the zeroth row. First row is the 2 1s here, that's the first row. 1, 2, 1 is the second row. I sort of remember it by the powers of 11. 11 to the 0 power is 1, 11 to the first power is 11, 11 to the second power is 121, 11 to the third power, you guessed it, is 1,331. So anyway, these are the rows, 0, 1, 2, 3. So the 6th row would be this one. Notice that this number here tells you what row you're on. So this would be the 8th row down here. This is the 7th row. The 6th row is this one. We also have entries in the triangle. So this is all of these are the 0th entry for each row, and all of these are the first entry of each row, and these are the second entry, and so forth. So the 4th entries are all of these infinite entries along that diagonal there. Okay, now that we have the rows and entries of Pascal's triangle under our belt, we're going to create a function. That's what we're here to talk about, is functions. You're thinking I was getting distracted. We're going to let n and k be whole numbers, with the distinction that k is always smaller than or equal to n. So we're only talking about whole numbers. That's 0, 1, 2, 3, 4, and so forth. And we're going to have a pair of them, n and k, where k is less than or smaller than n. Less than or equal to n. So, and we're going to call this set of all the possible ordered pairs where these are whole numbers and k is smaller than n or equal to n. We're going to call that set C. Then we're going to call set P all of the numbers that appear in Pascal's triangle. And we're going to talk about a mapping from this set to this set. That's what functions are. Functions take elements from a set called the input set or the domain and map them or transform them into elements that belong to some other set called the codomain. So this is going to be our domain, C, the ordered pairs of whole numbers. And P is going to be our codomain, and our codomain are numbers in the Pascal's triangle. So this is our target set. We're trying to get to numbers in the Pascal's triangle given two whole numbers. Now the name of this function is going to be called the lottery function, so I'll use L to represent it. And L is going to map elements in C to elements in P. So we're going to go from C to P. And we're going to do that by following a very simple rule. We're going to go to the nth row and pick the kth entry. Nth row, kth entry. And that, ladies and gentlemen, is a function. Let's see it in action. So here's some notation. L maps from C to P. So this is the domain, the input set, and this is the codomain, the target set. We cannot call this the output set necessarily. The range is the output set, and the range is either this set or a smaller subset. In this example, the codomain is the range, but we can talk about that in some later video. Now, what we're going to do, the way we pick up C, remember C was ordered pairs of whole numbers, and we're going to map that ordered pair of whole numbers to the kth entry on the nth row of Pascal's triangle. So, to do, we can't see that too clearly, to do 4, 2, for the lottery function to map 4, 2, it's going to go to the fourth row. Here's the fourth row. And it's going to pick the second entry. Remember, this is a zeroth entry, first entry, second entry. We always start counting from 0 in this triangle for some reason. Well, I know why, but we'll glance over it. Zeroth row, first row, second row, third row, fourth row, zeroth entry, first entry, second entry. So we go for the fourth row, second entry, we get the number 6, and that's how we do the mapping. So the lottery function takes 4, 2, and maps it to 6. Yay! Well, that was kind of complicated. Is there a nice formula for this? Can we put some algebraic formula over here so we don't have to build the whole triangle and then count? Is there some nice formula? Yes, but it requires you know factorial. 5 factorial is 5 times 4 times 3 times 2 times 1, you stop. And this works for every whole number except 0. 0 factorial, we just define to be 1. This little exclamation point is the operator symbol for factorial. So it makes a lot of nice jokes. 0! No, that's 0 factorial, not 0 with excitement. And it's equal to 1. Now, we're going to take our lottery function. We're going to map nk. And the way we do it is there's a nice formula. It's n factorial over k factorial times the difference between n and k factorial. So in our case, it's 4 factorial over 2 factorial times the difference in 4 and 2 factorial. So 4 factorial is 4 times 3 times 2 times 1. 2 factorial is 2 times 1. The difference of 4 and 2 is 2. These 2 times 1s cancel. So I have 2 factorial, which is 2 times 1. But wait, 2 goes into 4 twice, so I have 2 times 3. 2 times 3 is 6. Oh, see, nice little formula. We got our 6 without having to draw the triangle. And if there's a formula, well, then there's an easy way to program it, and then you can program a calculator. We won't use calculators. We might learn to program them. Why is this called the lottery function? That's a good question. Like, what in the world does this have to do with the lottery? Well, let's get a little lotto card. Let's say we were playing a lotto game where we pick 2 from 4 numbers. We win if we pick 2 numbers, and then the lotto people, they pick 2 numbers, and our 2 numbers match their 2 numbers. Yay, we win the lotto. Wouldn't that be a nice lotto game? I wonder if they'd still give out millions. Okay, so we have 4 numbers, so that's n equals 4. And we're going to choose 2 of them, that's k equals 2. Now, it should equal 6. If it's the lottery function, it should take us to 6. Well, the question is, how many ways could I pick 2 numbers from 4? In other words, how many lotto possibilities are there? Well, I could pick 1 with 2, 1 with 3, and 1 with 4. And you might think, well, what about 2 and 1? But remember, we're circling. So if you circle 1 and then you circle 2, they have no way of knowing if you circle 2 and then 1. So 2, 1 is the same thing as 1, 2 in the lotto game. So the order doesn't matter here. But so once I have 1, 2, 1, 3, 1, 4, I've got all the ones with 1 in them. But what about 2, 3, and 2, 4? Okay, there's 2 more. Now I've got all the ones with 2 in them. And then there's still 1 more with that's 3, 4 right there. And those are the 6 possible selections in this lotto game. So you see, 4 numbers, choose 2, maps to 6. Hence it's called the lottery function. Math made simple at Simpson Math.